Hi, welcome to the video on acetoacetate chemistry, which in the hindsight, I almost kind of regret that I separated this as a standalone different section from the malonate ester chemistry here that we did go over in class, because it's essentially really the same thing. And I want you to notice the contrast, right? In malonate ester, there's two carbonyls beta to each other, okay, and then both of them are esters. So on this right hand side there's an ester on the left hand side. Acetoacetate ester, there's an ester on this side, but it's a ketone on the other side. So that's really the only difference. So remember, in malonate chemistry there was an ester here, or oxygen I should say. So that would have, in the malonate chemistry, it would have become a carboxylic acid. In other words, this highlighted carbon would have been OH, or carboxylic acid. So that was, see, that's the same equivalent atom. That equivalent atom here that I just highlighted is now a carbon, so therefore you end up with a ketone. So the malonate chemistry was a good chemistry to make carboxylic acids with. Acetoacetate Claisen reactions are good chemistry to make different ketones with. So that's the only difference here. And the same idea, this portion of the molecule that's circled with green gets retained in the product, whereas this carbon here becomes decarboxylated, which means become a carbon dioxide, evolves away to be gone. And like we talked about in the last malonate reaction, you can use a different alkyl group with a different leaving groups and whatnot, or good leaving group I should say, to alkylate the alpha position so that you can incorporate different groups here, the orange part. So you can make, really, if you swap that orange part out, you can make any ketone you want. It's really helpful, a useful and effective synthetic method, and the chemistry works the same. I want you to make contrast, right? This enolate, I guess I skipped the first step where the alpha proton is being removed by the alkoxide. This enolate would be formed just like how this malonate enolate is formed, same chemistry. And that enolate is nucleophilic enough to do an SN2 reaction and forming this bond, after which it can undergo hydrolysis. And again, I would refer you to chapter 20 for the mechanism for that, the hydrolysis of the ester right here to the corresponding carboxylic acid. Remember that at high temperature, because of the, maybe I'll emphasize the high temperature here, right, that encourages higher entropy, and the entropy would be increased more if you can generate gas, another particle, or especially in the form of a gas like carbon dioxide that can evolve away. And so for that reason, this sort of electrocyclic reaction happens to eliminate carbon dioxide, which is right here. And that would leave an enol. This is enol that readily tautomerizes to the keto form, and that would be the product. Okay. Now, before we take a look at the example below, you might want to pause the video and then see if you can predict the product. And I trust that maybe you've done that just now. There is actually, pardon me for this, typo for that. This should be sodium methoxide, otherwise you would have a transesterification issue here. So please correct that mistake. But again, you would form an enolate. This carbon would be nucleophilic, which would do SN2 with this dibromobutane. So you would end up with this monobromobutane, right, attached at the alpha position. This carbon had the bromide earlier. And if you treat this with potassium T-butoxide, you would remove the remaining alpha proton there because that's a strong base. And remember that alpha proton is particularly acidic, like a pH of 10 or so. That enolate can then cyclize onto the other bromide right there. So that happens to form this cyclic alkane. This happens to be a 5-membered ring because there's 1, 2, 3, 4, 5 carbons there, starting from the enolate. And remember, treatment with the strong acid and heat encourages hydrolysis of the ester to the carboxylic acid, which can decarboxylate, leaving behind the ketone. Okay, so that's the product.